All right, friends, welcome back. Happy Friday. This is the last of 3 lectures. Let's see, some of you have been asking what we're going to get to before the end. I think it will take us today and Monday to get through chapter 28 and maybe even a little bit beyond that. If we do anything in any of the remaining chapters, it'll be on Wednesday. It'll be about polymers. There won't be any new mechanisms, and I'll basically just be showing you, taking you on a tour through the wide and marvelous world of plastics and dental composite and Kevlar, so that you can get a sense for what polymers are. All right, let's go ahead and begin. Last time we were talking about the Suzuki reaction. This is the reaction of a vinyl, or rather an aryl halide with either an aryl or vinyl boronic ester. And the kind of bond that we're making is a bond between two sp2 hybridized carbons. You've got one that's aryl in this case, and the other is vinyl, but the purple one could also be a benzene ring. So the catalyst that we use is this Palladium Zero species. It starts out as palladium tetrakis triphenylphosphine. And right now, you can tell it's Palladium Zero because these are all L ligands that leave as neutral molecules. That means palladium itself is neutral because there's no charge on the complex. Palladium comes with 10 valence electrons, so that's a D10 metal. And if you count overall 10 on palladium and 2, 4, 6, 8 from the ligands, this thing already has 18 electrons. We call that coordinatively saturated. That means the valence shell is full. This is like a noble gas configuration. So there's no chemistry that can happen yet. The catalysis can't happen yet until a couple of those ligands dissociate. Removal of 2 of those phosphine ligands gives you still a Palladium Zero species, still D10, but now there's only 2 L ligands, so it's a 14 electron complex. Now there's room for other stuff. So the oxidative addition step, as we talked about last time, is a pair of electrons from palladium. 2 of those D electrons form a new bond with carbon, and then the electrons in the bond between carbon and halide form a new bond between halide and palladium. Once that's done, both of those bonds belong to their respective X ligands. Both of those pairs of electrons belong to those X ligands. So palladium has formally lost 2 electrons, and that's why we call this an oxidative addition step. If you count these electrons as belonging to the X ligands, the palladium has 8 d electrons instead of 10. If you reflect on the fact that this is neutral, and both of these are X-type ligands that would leave as negatively charged, palladium has to have a +2 charge, so that now gives us the Palladium-2 species. Next, we're going to swap out the vinyl portion of the boronic ester for the halide, or we're going to swap out the halide for the vinyl portion of the boronic ester or acid. So this is literally just a handoff between ligands between boron and palladium. Bromine leaves and makes a new bond with boron, and then the vinyl ligand gets transferred directly to palladium. Nothing changes in oxidation state. This is just a ligand swap. We call it transmetallation because we're thinking of both palladium. Palladium is a metal. Boron is an honorary metal. I don't know. So they're trading ligands. The vinyl ligand ends up on the palladium, but we haven't changed palladium's oxidation state. When you have these 2 carbon X-type ligands close to each other, then electrons can come from one of the carbon-palladium bonds and attack the other sp2 carbon and then electrons in the carbon-palladium bond there can go back onto the metal. That releases our product and takes you back to your starting catalyst, which is again a D10 Palladium Zero species. And so this catalytic cycle turns, and it can turn over many, many, many times. So you only need a fraction of a percent of your starting materials. A fraction of the percent of those can be the palladium catalyst. All right, questions about that catalytic cycle? Go ahead.
Does it need to be an aryl and a vinyl, or can it be two aryls, two vinyls?
Can it be two vinyls? No, in general, and I don't know why, but it can be two aryls. So an example of two aryls would be this reaction, which I think we talked about a little bit last time. You have this aryl halide, this aryl boronic ester, and you can make the bond quite easily between the two benzene rings. And so far, this is the only way that we've learned this year how to make a bond directly between benzene rings. So here's the vinyl, or I'm sorry, the aryl halide portion, and here's the aryl boronic ester portion. Yeah?
Is there a reason why the stereochemistry of that bonds is
Is there a reason why the stereochemistry, if it's a vinyl halide, yeah, the stereochemistry is preserved? I think because you never have a free carbanion. A vinyl carbanion is a little bit interesting. It would basically be like this. It would basically be sort of sp hybridized, and you could imagine losing stereochemistry, but you never really have that. It's sort of a direct handoff. That's hand waving. I don't exactly know, but you can think of it that way. Okay, what else? All right. There are, for synthesis kind of questions, it's good to have an idea of where you can get these reagents from. The aryl halide you can get very easily from benzene using electrophilic aromatic substitution, right? That's the aryl bromination reaction that we learned early on this semester. If you want the aryl boronic ester, you still need this, but you convert it to the organolithium reagent, and then you use this boron reagent. It's only got 3 groups on it, so there's still an empty p orbital there. The electrons in this carbon-lithium bond attack the boron to give you this sp3 hybridized boron species that's negatively charged. To avoid that negative charge, one of the methoxy groups leave, and that gives you your boronic ester with your aryl group attached. And this is the carbon that you're going to make the new bond with. If you want a vinyl boronic ester, then the method of choice is to start with this alkyne and then do hydroboration. So this is a revisit of a reaction from 351. It's a syn addition of hydrogen and boron across one of these pi bonds. The hydrogen ends up on the more substituted carbon. The boron ends up on the less substituted carbon. They are added on the same side. And what that means is the boron is always trans to the R group. If you wanted to make a Suzuki reagent in which the boron was cis to the R group, you'd have to use a different method, and I don't think I know how to do that. All right, so one interesting thing to think about is that this bond between two arenes has some interesting stereochemical properties, which we're not going to talk about, but basically those orthohydrogens bump into each other. So this ring system is not planar. In fact, they have to twist out of plane and basically be sort of perpendicular to each other to avoid those steric problems. That introduces the possibility for something called axial chirality, which we are not going to worry about. But it is out there, so if you ever hear about it. But just understand when you see two benzene rings linked together directly, it's not flat, they're twisted. And that twisting can have some important consequences. So this reaction is used all over the place in pharmaceutical chemistry to make drug molecules because it's highly efficient and you can run it on a kilogram scale. So you don't have to write any of this down. I just want to show you an example of something in industry that's made via a Suzuki reaction. So you get a sense of the tolerance of the Suzuki reaction to different functional groups. Here is the key bi-aryl linkage. That means two arenes attached directly to each other. And then the rest of it's a little bit weird. This is a molecule that was involved in phase 3 clinical trials for, it's a beta secretase inhibitor, and beta secretase is the protease that clips off the amyloid beta peptide from the amyloid amyloid peptide precursor, APP protein. And of course, amyloid beta is associated with aggregates of amyloid beta are found in the brains of Alzheimer's patients. And so inhibiting that process was thought to be a useful therapeutic strategy. That whole thing is controversial. You can read all about it. But for right now, just accept the fact that this is a drug candidate called lanabecestat. I don't know where they come up with these things. Usually focus groups, actually. They try to come up with a name that sounds cool and scientifically, but doesn't sound scary or gross. And this was developed by the AstraZeneca. So that's a drug company. I think it's British, but they have places in the United States. In any case, here is the key bond. And they were able to make this from the corresponding starting materials. They made the boronic ester on the side of the pyridine ring. And there's a little bit more to it than that, but that's sort of where I'll leave it. Here is the alkyne. And then the other reactive partner was just this portion with a halide here. And these are the two carbons that they linked together. They were able to do this with a catalytic amount of Palladium Zero. They needed some base, they needed to cook it, but 100 kilogram scale. So just so you know, the typical types of chemistry that we do in the fume hoods on the 4th floor in the organic area, at most we'll be making a gram or two, and that's even usually highly unusual. So 100 kilos is like an astronomical amount. And the fact that this reaction works both in the fume hood on a small scale and then in the chemical industry in a big reactor on a massive scale is really impressive. Also, the functional group tolerance, notice you've got this amino group here. It's adjacent to a benzene ring, but you don't have to protect it to do the reaction. It doesn't interfere. And so this is a very useful reaction in drug discovery. The biphenyl or bi-aryl linkages are found all over, and it's a really great way to do what's called diversity-oriented synthesis, where suppose you have 10 different boronic acids and 10 different aryl halides. You can easily generate 100 new compounds with only 20 different starting materials because of this coupling reaction. Did we just lose a light? Suddenly it got dark out there. Okay, that's the Suzuki reaction. Okay. Sorry about that. So, fortunately, what we missed was just a review of what we were talking about last time. All right. Anything you want to ask about the Suzuki reaction, catalytic cycle? You should be comfortable with the mechanism. You should be able to predict products. You should be able to provide reagents. You should be able to think about a synthesis. Think about a synthesis in a retro sense. What would be the starting materials required to make this molecule via a Suzuki reaction? All right. Yes, go ahead.
So does the palladium ever gain back its original phospho groups, or does it keep going with just two?
Yeah, so that's a really good question. Does the palladium ever gain back its two phospholigands? This is an equilibrium, so I think there's some amount of this that is always present. People do what are called kinetic studies, where they vary the concentrations of starting material and catalyst, and they see how that affects the rate of the reaction. And from that, you can determine what's called a resting state of the catalyst, which is where does the catalyst spend most of the time. And I don't actually know where that is at this stage. Presumably, yes, there is some equilibrium between the catalyst and the starting material, but you've got enough of the catalyst to make the reaction crank and go. Yeah. What else? Yeah.
Does it matter how many things are on that benzene ring to do the
Does it matter how many things are on the benzene ring to do the reaction? There's probably some limits, maybe because of sterics, but frankly, the linkage between two benzene rings is pretty sterically hindered anyway. You may not necessarily appreciate this, but if we draw in the carbon-hydrogen bonds, they actually are bumping into each other if that thing is planar. So for those aryl-aryl linkages, they twist out of plane, so those rings are sort of perpendicular to each other. That introduces something called axial chirality, which we don't want to talk about. So sterically, this reaction is pretty tolerant of it anyway. I could imagine that if you have substituents here at these ortho positions, it might be a problem, but I think you can do whatever you want at the others. Okay, what else? Yeah?
In the step where we're creating the carbon sigma bond, does it matter which set of electrons is
Right, in this reductive elimination step where we're making the carbon-carbon sigma bond, does it matter which electrons do the attacking and which end up on palladium? No, you can't tell. In fact, that's one of the sort of rules of molecular orbital theory. You can't actually tell one electron from another because they're identical particles. Yeah, okay, what else? Okay, so let's go on to another kind of palladium reaction. This is a coupling reaction as well. We're going to click two different sp2 hybridized bonds together, rather carbons together, but the players are going to be a little bit different. And this reaction was discovered and named after Professor Heck. So kind of fun. The last name Heck makes me think of the show The Middle. Anybody ever watched that vaguely? Yeah. When COVID hit and we were all at home all the time, we started watching that show at night with our boys, and it was sort of we look back on it with fondness because that was the one time in the past couple of years where we've all been together. Now my son's off at college and the 16-year-old's working and the 14-year-old is like always with friends and the 10-year-old is like always with friends. So suddenly I'm like an empty nester, which is really, really bizarre. So I appreciate the chance to come here and interact with all of you, my surrogate children. Okay, the Heck reaction is the reaction of an aryl halide. Okay, so same kind of one partner as the Suzuki reaction. I'm just giving you a specific example. And then a vinyl group, only unlike the Suzuki reaction, you don't need there to be a boron on the vinyl carbon. It can just be the these CH bonds. Now, normally the general pattern is some kind of group where Z is an electron withdrawing group. The chemistry generally works best for that. Over here, you could have an aryl halide, and the reaction actually works for vinyl halides as well. So the substrate scope is a little bit different. The catalyst that you put in, the standard thing that works, is a little different. Instead of being a Palladium Zero species, it's Palladium 2. Oh, holy Toledo, where did that double bond come from? Sorry, folks. Yeah. It's Palladium 2 acetate, which we've talked about before, where you have an X ligand here, and then the carbonyl oxygen is an L ligand. This is Palladium 2. And you need phosphine ligands as well. The phosphine ligand that's chosen is a very sterically hindered one where you have methyl groups. It's going weird with the Apple Pencil, sorry. The phosphine ligand is, we can't decide on a line thickness. I'm going to draw just one of the groups on the phosphine ligand, and then we're going to do this. This is called an ortho-toluyl group. It's like toluene, except you've got the phosphine that's ortho to the methyl group. Incidentally, there's a whole wide world of phosphine ligands out there that help control reactivity. For us, we're just thinking in terms of, okay, they bind the metal, but they actually do influence the electronic properties of the metal and the steric environment. So don't get too hung up on what this group is or what it has to be. It's just sort of an R group. But understand that in the whole world of organometallic chemistry, it's like a cottage industry to generate new phosphine ligands that tweak the reaction in a little bit, in a strange way. And then you need a base, which in this case is usually triethylamine. So those are the reagent conditions, but the effect of the reaction is going to be similar. We take the sp2 carbon of the aryl/vinyl halide, and we link it to the sp2 carbon of the alkene, and we get a new carbon-carbon bond. And there's an interesting stereochemical issue here. Notice that the olefin, the alkene, is monosubstituted on this side. On the side we're going to make the bond with, you just have two CH groups. So you have the possibility to make either the cis or the trans isomer, and you only get the trans isomer. And that has to do with a mechanistic step that generates the product. So we're going to exclusively see E or trans stereochemistry in the products, and this is the new bond that we've made. Okay? Just so we get substrate scope down, let me give you another example. Here is a vinyl bromide, sp2 carbon, and then here is another olefin with an electron withdrawing group on it. I'm going to use these same conditions, and that's going to make a new bond. And you're going to continue to get the trans stereochemistry with respect to this new bond that you've made. This gets a little bit tricky, folks, because sometimes people will say, okay, the Heck reaction only gives you trans stereochemistry, and then they're going to start with a vinyl halide like this, and then try to say that it gives you this where everything is trans. That's not true. The stereochemistry on the vinyl halide remains unchanged. It's the stereochemistry on the olefin for the new bond that we're making that that has to be trans. So again, in red, I'm going to highlight the new bond that we're making, and then the electron withdrawing group is going to be trans to that new bond. Do you see the distinction? The new bond that you make is trans to the electron withdrawing group on the olefin. It's not that all of the double bonds are trans. The stereochemistry on the vinyl halide is unchanged. Okay. By the way, look at that product. It's a 1,3-diene. 1,3-dienes we can use in Diels-Alder reactions. So now your worst nightmare, we can do a synthesis where we start from simple starting materials, we generate a diene, and then we do a Diels-Alder reaction to make, dun, 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 a 6-membered ring, right? Can we see one of those? Yes. So remember, to do a Diels-Alder reaction, you would need to draw the molecule in its S-cis conformation. The cyanide group is going to be here. Both of these, in this case, double bonds are trans, so we'd have that. Now, can you see how you do a Diels-Alder reaction? If, I don't know what the... You need some dienophile. I'm not sure this reaction would work. I'm just sort of demonstrating it. Here is your Diels-Alder product. Where I'm not showing you stereochemistry, but that's the idea. These two groups would have to be cis to each other. These two groups would also have to be cis to each other, and then you've got other diastereomers. Fine. So you could have either the exo or the endo stereoisomers, plus their respective enantiomers. Anyway, you can see how you could use this in a longer synthesis. Yeah?
Just as a refresher, how would you change the original reaction product into the Diels-Alder one? Because you don't have free rotation around that.
So yeah, the question is, how do you get from this conformation is called the S-cis conformation. This is called, oh, sorry, no, backwards. This one's called the S-trans configuration. S is for sigma bond, S-cis. You're right that because of conjugation, rotation around this bond should be restricted, but you can access, the barrier is low enough that you can get from the S-trans to the S-cis. Yep. So no reaction is necessary, that's just rotation. Okay, what else? Now you have to remember all that Diels-Alder stuff. At least I warned you, right? Spring that one on you in a surprise way. All right, let's talk about mechanism for that Heck reaction. So you'll notice that the catalyst, or what we put into the reaction mixture, is this Palladium 2 species. And why do we do that? I don't know, because the actual active catalyst is a Palladium Zero species. This is an issue your text doesn't address, and it's kind of weird. They say just, oh, yeah, it's just we put in Palladium 2 for undisclosed reasons, and then it somehow becomes Palladium 1. In reality, what likely happens is that you do this in water, and so here we have the I'm not actually sure what to do here. Probably you lose the acetate ligands, and probably you get 2 of those phosphine ligands. which I'm just going to call PR3 instead of trying to abbreviate them. This is still a 2+ complex. Probably you have water come and bind like this, and then probably get deprotonated, which would take this down just to a regular plus complex. Then actually one of the phosphine ligands can attack the oxygen and reduce the metal, and that would get us down to a Palladium Zero species. I think, folks, it may be time to retire the old Apple Pencil. This thing's giving me trouble today. By the way, that all that was just for your edification. I don't care that you memorize that or know that. But if you were wondering, how on earth does Palladium 2 become Palladium 0? It gets reduced by one of the phosphine ligands. All right. With that in mind, our catalytic cycle is going to start with the Palladium 0, which will represent like this. Again, Palladium 0 is a D10 complex, and right now we have 14 electrons in the complex. What will happen first is oxidative addition of the aryl halide. So I'm going to show that with just, we'll use a phenyl group and Br. Again, we will take 2 electrons from the metal to make a new carbon-carbon bond with to make a new carbon-palladium bond, and then the electrons from the carbon-bromide bond will go on to the metal. So that is an oxidative addition step. And you can tell that it's oxidative addition because after it, we have 2 X ligands. As we said before, irregardless of where the electrons come from, once they're in a bond with an X ligand or an L ligand, they belong to the ligand. So this is now Palladium 2. Palladium now has only 8 d electrons, and but it is now a 16 electron complex. So we've added the benzene ring, or we've added the aryl halide. It's very important here that this is a 16 electron complex, because instead of doing transmetallation, remember in the Suzuki reaction, boron came and swapped out the vinyl group for the halide. But with our reactive partner in the Heck reaction, it's just, say, this alkene. We don't have a boron to do the transmetallation. So the mechanism is actually a little bit different. What happens, I'll just put an R there, maybe a Z for the electron withdrawing group. The olefin binds to the metal and forms what's called, well, with the alkene acting as an L ligand. So this is going to involve one of those weird, one of those weird bonds that actually doesn't represent any electrons. Actually, I'll use a dotted line pointing towards the pi bond. And then here is the Z group. So just to keep track of the ligands, you have 2 L ligands, you have 2 X ligands, and then the fifth ligand comes from this pi bond. Palladium is still palladium 2. Man, that's irritating me. Why can't we figure that out? Am I imagining that? It's like giving me really, really thin lines randomly. All right, this is still palladium 2. Palladium still has only 8 d electrons, but now if you count electrons, there's the 8 on palladium, then 2, 4, 6, 8, 10. So now we're at an 18 electron complex. So now this is what we call the palladium is coordinatively saturated. There's no room for anything else. Okay, so what is going to happen next? And I guess we would call this step just ligand binding. What's going to happen next is a new mechanistic step that we haven't talked about yet. And this mechanistic step is called migratory insertion. And I suppose it'll be better if I draw the Z group on the other side, but it doesn't matter. So what is migratory insertion? This involves the carbon-palladium bond here between the aryl group and palladium attacking the terminal vinyl carbon of the olefin. Okay, you can think of that as maybe attacking the pi star, and then the electrons in the pi bond go and attack palladium. Okay, that mechanistic step is called migratory insertion. And what this does is it replaces the aryl group on the palladium with the internal carbon from the olefin. So here is the new bond we made between the sp2 hybridized carbons of the benzene ring, carbon of the benzene ring, and then what used to be the olefin, the terminal atom on the olefin. All right, let me pause there because I know that's a bit confusing, and just let's review where the bonds come from. Okay, the bond between the benzene ring and the terminal carbon of the olefin comes as this X ligand takes its electrons and attacks that carbon. Remember that carbon has 2 hydrogens that are not shown. If we stopped there, we'd have too many bonds to carbon, so we must break the pi bond and have that pi bond attack the palladium. Incidentally, this is why it's good to have an electron withdrawing group here, because in the transition state, there is a buildup of negative charge on that internal carbon, and that electron withdrawing group can stabilize it. So that after the reaction, we're attached to the metal, and it's still an X ligand, but we're attached to the metal through that internal carbon of our olefin. And maybe it would be helpful just to number things. The benzene ring goes on carbon 1. Carbon 2 is now bonded to the metal. Okay, questions about that? So that's not oxidative addition, it's not reductive elimination. If you look at it, it's still Palladium 2 after this reaction. It's still a D8 complex. The difference is that now it's only a 16 electron complex. Okay. All right, well, that's the carbon-carbon bond, but you'll notice that if we go back up to the products, it's supposed to stay a double bond over here on the olefin side. But we just got rid of that double bond. So therefore what? What happens? All right. So what happens next, I'm going to redraw this complex, but in a way that's going to show you where the trans stereochemistry comes from. So let's just suppose that the Z group is back. We have to have one of the hydrogen atoms sort of eclipsed with the carbon-palladium bond for this reaction to work. And so the more stable conformation is one that puts the phenyl group not eclipsed with the Z group. We can draw the other hydrogen on this carbon and the other hydrogen here. Do you see that if we looked down this bond between carbon and carbon, that's carbons 1 and carbon 2, do you see that it would be better to have phenyl eclipsed with this hydrogen than to have phenyl eclipsed with the Z group? Yeah. Okay. Well, what happens next is a new mechanistic step that we also haven't talked about. That mechanistic step is called beta hydride elimination. And it's interesting. It's almost reminiscent of an oxidation step using NAD plus in the sense that we're going to have electrons from this X ligand kick down and make a double bond. And again, that would require this hydrogen to be a leaving group, which hydride is a terrible, terrible leaving group, but it's not so much leaving as it is being directly handed off to the metal. The reason it's called beta hydride elimination is because relative to the metal, this is the alpha carbon and this is the beta carbon. Beta hydride elimination, and what that does is it then releases our product, and if you pay attention to that, as I said, the active conformation is one where the hydride that's going to get delivered is eclipsed with the metal carbon bond. And so in the transition state that makes this double bond, the phenyl group and the R group on the olefin are on opposite sides. And so the olefin that forms in that step is going to be the trans olefin. This is still the new bond that we made. And then here is the benzene ring. So that, I'm sort of running out of space in our catalytic cycle. That's our product. But the complex after this beta hydride elimination is still a palladium 2 complex. And so now our task is to reduce that palladium 2 complex back. I've just written R there 3 times in a row while meaning to write P for phosphorus. It is very difficult for me to talk and draw at the same time. My wife has told me she's just floored that I can pull this off. You could tell her, though, that I don't actually do it that well. And so this is now still a palladium 2 complex. we still have 2 X ligands, and it's still a 16 electron complex. What happens next, and this is where our base comes in, our base is going to deprotonate the palladium complex. That's going to take the electrons that used to belong to that X ligand, and that's going to put them back on palladium. And at the same time, bromine is going to leave. And you could also have drawn this step as though the hydrogen or the bromine attacked the hydrogen and the electrons in the carbon-hydrogen bond went back on the metal, and then afterwards the deprotonation occurred. It really doesn't matter how you do this. They're basically equivalent. I'll draw it this way because that seems to make the most sense. But this is formally a reductive elimination step, and also deprotonation of an acid to give an acid and a conjugate base. And so your product forms in that step. You make an equivalent of the conjugate acid of your base and Br minus. So you do need a full equivalent of base to make this reaction go, but that completes our catalytic cycle. That one was bad. I think that's worse than the Suzuki reaction because it involves more steps and there's a stereochemical issue. So, questions? Yeah. Why does the bromine come off at the end? You need it to so that you can do the first oxidative addition step. We want to get back to a 14 electron complex to make the oxidative addition step favorable. Technically, there would be room for another bromine to hang out there, and it might, but at least the way it's shown in the textbook is that the bromine comes off. But you're right. That's just whether or not this bromine is on there. It's let's see. After you do the reduction, if bromine was still on there, the complex would be negatively charged. So I think to avoid that, the bromine dissociates. Because this is a reductive elimination step. We used to be palladium 2, but these electrons that belong to the X ligand now go back on palladium. So now we go back to a D10 Palladium Zero. I don't think I answered your question. Why does the bromine come off? So that after the reductive elimination, the complex can be neutral. All right, what else? Okay, so be able to do this in a retrosynthesis sense, be able to use it in predict the products, be able to understand the mechanism. Okay, no questions because I'm about to unleash some more horrors upon you. So, for goodness sake, delay me. Yes?
Why do we have equilibrium? How do you go forward versus...
Yeah, so these are equilibrium arrows. How do you go forward versus backward? It turns out when you do the kinetic experiments, you figure out which of these steps is fast versus slow. I suppose that it's fine for us to just consider this going in the forward direction because it works. Likely some of these steps are reversible, and then there's a rate determining step that's irreversible, and then everything after that goes forward. There was nothing to learn, nothing tricky to learn from those equilibrium arrows. Yeah. Okay, what else? Yes? Does it have to be that specific base? No, you could use, I think the amine base works best, but I think amine would work. I think probably it needs to be a tertiary amine. But I don't actually know why. So Yeah.
So why would someone use the Heck reaction versus
Why would someone use the Heck versus the Suzuki? What? The Heck? That's going to die. It's a dumb joke. Just because you don't have to go to the trouble of making the boronic ester. So there would be practical reasons for doing one versus the other in terms of how easy it is to make the olefin that you need versus the boronic ester that you need. Yeah.
What video games are you playing?
What?
What video games are you playing?
What video games was I playing? Oh, the Lego Star Wars. I have completed the Phantom Menace and the Attack of the Clones. But I still have like 7 episodes to go. So, all right. See you Monday.